A haloalkane molecule is formed when a hydrogen atom in an alkane molecule is replaced by a halogen atom. Some typical haloalkanes are illustrated here. This class of compounds is also called alkyl halides. Haloarenes are formed when a hydrogen atom in an aromatic compound, such as benzene, is replaced by a halogen atom. These compounds are also called aryl halides. Many organic compounds that contain halogens occur naturally. Both synthetic and naturally occurring halogenated organic compounds have important uses in medicine and research. Chloramphenicol is a naturally occurring substance produced by soil microorganisms. As you can see in the structural formula, it contains 2 chlorine atoms. Chloramphenicol is used as an effective drug in the treatment for typhoid fever. The thyroid gland, a butterfly-shaped gland at the base of your neck, produces the hormone thyroxine. Notice the 4 iodine atoms in the chemical formula. A lack of dietary iodine can lead to a deficiency of this hormone, which can eventually lead to goiter. Many countries have mandated that small amounts of iodine be added to table salt to minimize the risk of goiter. Chloroquine, a synthetic compound, is used for the treatment of malaria. Halothane is used as a general anesthetic during surgery. These compounds are used in industries as solvents for relatively non-polar compounds, and also as starting material for the synthesis of a variety of organic compounds. Haloalkanes and haloarenes can be classified in several ways. One way is to classify them based on the number of halogen atoms. Chloroethane, a monohaloalkane, and chlorobenzene, a monohaloarene, each containing 1 halogen atom, are shown here. Dihaloalkanes and dihaloarenes have 2 halogen atoms in their formulae. Trihaloalkanes and trihaloarenes with 3 halogen atoms are also known to exist. Based on the hybridization of the carbon atom to which the halogen atom is bonded, monohalo compounds are classified as alkyl halides, allylic halides, benzylic halides, vinylic halides, and aryl halides. In alkyl, allyl, and benzyl halides, the halogen atom is attached to an sp3 hybridized carbon atom. On the other hand, in vinyl and aryl halides, the halogen atom is attached to an sp2 hybridized carbon atom. We'll start with the alkyl halides, or haloalkanes, which have the general formula Rx. R here represents an alkyl group. In these compounds, the halogen atom is bonded to an sp3 hybridized carbon atom. The homologous series of alkyl halides can be represented by the formula CnH2n plus 1x. based on the nature of the carbon atom to which the halogen atom is attached. The alkyl halides are further classified into primary, secondary, and tertiary. In primary alkyl halides, the halogen atom is attached to a primary carbon atom. For example, ethyl chloride is a primary alkyl halide. In secondary alkyl halides, the halogen atom is attached to a secondary carbon atom. Isopropyl chloride shown here is a secondary alkyl halide. In tertiary alkyl halides, the halogen atom is attached to a tertiary carbon atom. For example, in tertiary butyl chloride, the chlorine atom is attached to a tertiary carbon atom. You need to be able to recognize allylic carbons. Allylic carbons are carbon atoms bonded to a carbon atom that is doubly bonded to another carbon atom. As the illustrations here show, allylic carbons are one position away from a double bond. Allylic carbons are sp3 hybridized. Allylic haloalkanes have halogen atoms attached to allylic carbons. In benzylic halides, the halogen atom is bonded to a carbon atom with sp3 hybridization, that is linked to an aromatic ring. In primary benzylic halides, the carbon attached to the halogen has only one carbon-carbon bond. Here are secondary and tertiary benzylic halides. In a secondary benzylic halide, the carbon attached to the halogen atom is bonded to two other carbons. In a tertiary benzylic halide, the attaching carbon is bonded to three other carbon atoms. It will be helpful in your chemistry studies if you can identify vinylic carbons, or alkenyl carbons, as they are sometimes called. Vinylic carbons are sp2 hybridized and are double bonded to one carbon atom. The vinylic carbons in two different molecules are shown in the illustrations here. Vinylic halides have a halogen atom bonded to an sp2 hybridized carbon atom of a carbon-carbon double bond. Two examples of vinylic halides are shown here. In aryl halides, the halogen atom is bonded to an sp2 hybridized carbon atom of an aromatic ring, as illustrated here. Learning the proper nomenclature of organic molecules is very important, and it takes a lot of practice. Many compounds have common names as well as systematic IUPAC names. The common names of alkyl chlorides can be found by giving the name of the alkyl group followed by the halide. In the IUPAC nomenclature system, they are named as halo-substituted hydrocarbons. Let's write the IUPAC name of the given molecule. The longest continuous carbon chain has 4 carbon atoms, and hence the root word is but. Since the longest carbon chain is saturated, the primary suffix is ane. Thus, the name of the parent carbon chain is butane. We then need to identify the substituent and its location. For this, we need to start numbering the carbon chain from the end nearer to the carbon atom to which the substituent is attached. We see that the carbon atom with the substituent chlorine is in position 1. Thus, the name of the given compound is 1-chlorobutane. Now try these practice problems on your own. Give the IUPAC names for these two molecules. Are they primary, secondary, or tertiary haloalkanes? The IUPAC name for the molecule on the left is 2-chloro-2-methylbutane. It is a tertiary haloalkane as the chlorine is bonded to a carbon linked to 3 other carbon atoms. The IUPAC name for the molecule on the right is 3-chlorohexane. It is a secondary haloalkane. Notice that the chlorine is bonded to a carbon linked to 2 other carbon atoms. Apply your skills in a new way. Draw the formulae for the compounds here. Try these on your own before checking the answers. The illustration on the left gives the trans isomer of 2,3-dibromobute-2-ene. Can you draw the cis isomer? Shown here is the cis isomer of 2,3-dibromobute-2-ene. The common names of haloarenes give the name of the aryl group followed by the halide. Common names may use the prefixes ortho, meta, and para to indicate relative spacing, 2, 3, or 4 carbons between the halogen atoms. In IUPAC nomenclature, haloarenes are named as substituted arenes, listing the location and type of the halogen atoms. Let's work through some practice problems together. What are the IUPAC names of these compounds? All 3 molecules are benzene derivatives. Remember that if more than one similar substituents are present, then we must give the location of each and include prefixes indicating the number present. The common and IUPAC name for molecule A is fluorobenzene. Molecule B is often called meta-dichlorobenzene. Its IUPAC name is 1,3-dichlorobenzene. The common name for molecule C is symmetrical trichlorobenzene, while its IUPAC name is 1,3,5-trichlorobenzene. Dihalogenated compounds with the same type of halogen atoms can be classified based on whether the halogen atoms are on the same or adjacent carbons. If the 2 halogen atoms are bonded to the same carbon atom, then it is called a geminal dihalide. Geminal dihalides in the common system are named alkylidene halides. In the IUPAC system, they are named 1,1-dihaloalkanes. Thus, the molecule shown here can be called ethylidene chloride. Its IUPAC name is 1,1-dichloroethane. If two halogen atoms of the same type are bonded to adjacent carbon atoms, it is called a vicinal dihalide. Vicinal dihalides in the common system are sometimes named alkaline dihalides. In the IUPAC system, they are named 1,2-dihaloalkanes. For the molecule shown here, the common name is ethylene dibromide. Its IUPAC name is 1,2-dibromoethane. Here are some additional practice problems. Try to name molecules A, B, and C on your own before proceeding. Molecule A is 1,1-dichlorocyclopentane. Molecule B is correctly named 2,4-dibromopentane. In this molecule, you will get the same name whether you start counting from the left or the right. Molecule C is 7-bromohept-1-ene. You might see this written as 7-bromo-1-heptene, using earlier IUPAC guidelines. The double bond takes priority over the halogen atom, so carbon number 1 is at the far right. Practice is the key to learning organic nomenclature. Here are 2 problems to try on your own. What are the common and IUPAC names of these compounds? Vinyl bromide and allyl chloride are the common names of these molecules. What are their IUPAC names? The common name of compound A is secondary butyl bromide, and its IUPAC name is 2-bromobutane. The common name of compound B is neopentyl bromide, and its IUPAC name is 1-bromo-2,2-dimethyl propane. The common name of compound C is tertiary butyl bromide, and its IUPAC name is 2-bromo-2-methyl propane. The IUPAC name for vinyl bromide is bromoethene. No number is necessary for the position of the bromine atom. Whichever carbon atom it is attached to must be the first carbon. The IUPAC name for allyl chloride is 3-chloropropene. Because of the double bond, the leftmost carbon is at position number 1. Let's practice another important skill. That is, drawing structural formulae from names. It is best if you start with the end of the name, with the carbon backbone, and work forwards. Try them independently before checking the answers. The correct structural formulae are shown here for 2-bromo-2-iodobutane and 1-fluoro-2-methyl-cyclohexene. Remember that if there is more than one substituent, they are listed alphabetically. Pure alkyl halides are colorless. For example, methyl bromide or bromomethane is a colorless gas that can be used as a pesticide. However, this use is being phased out due to its toxicity. Historically, it was used as an industrial fire extinguishing agent. Methyl bromide is also known to be an ozone-depleting chemical. The alkyl bromides and alkyl iodides may develop a color when exposed to light. For example, ethyl bromide turns yellow when exposed to light and air. Many volatile alkyl halides have a sweet smell, but this may not be noticeable unless the concentration is relatively high. Lower alkyl halides, including methyl chloride, methyl bromide and ethyl chloride, as well as some chlorofluoromethanes, are gases at room temperature. Higher alkyl halides are liquids or solids. You have already studied that the carbon-halogen bond in halogen compounds is polar. Due to the greater polarity and higher molecular mass of haloalkanes as compared to the parent hydrocarbons, the dipole-dipole and van der Waals forces of attraction are stronger in these compounds. Hence, haloalkanes have considerably higher boiling points than those of hydrocarbons of comparable molecular mass. For a given alkyl group, the boiling point increases with increasing atomic weight of the halogen. This is due to an increase in the magnitude of van der Waals forces of attraction with an increase in size and mass of the halogen atom. Thus, among the alkyl halides, alkyl iodides have the highest and alkyl fluorides have the lowest boiling points. For a given halogen, the boiling point increases with an increase in the number of carbon atoms in the chain. This is again due to the increase in the magnitude of van der Waals forces of attraction with an increase in the size of the carbon chain. The boiling points of isomeric haloalkanes decrease with an increase in branching. This is due to the fact that with an increase in branching, the molecule attains spherical shape with less surface area. This results in a decrease in the magnitude of van der Waals forces and hence the decrease in boiling point. Thus, among the isomeric butyl chlorides, the straight-chain isomer, N-butyl chloride, has the highest, while tertiary butyl chloride has the lowest boiling point. The haloalkanes are only very slightly soluble in water. Why? For a haloalkane to dissolve in water, energy is required to break the attraction between the haloalkane molecules and the hydrogen bonds between the water molecules. As new attractions between the haloalkane and water aren't nearly as strong as the original hydrogen bonds in water, less energy is released during this process. Thus, haloalkanes are sparingly soluble in water. Haloalkanes do tend to dissolve in organic solvents. The intermolecular attractions that form between haloalkanes and the solvent molecules have similar strengths as the attractions being broken in the separate haloalkane and solvent molecules. Alkyl fluorides and alkyl chlorides are less dense than water. In a mixture with water, alkyl fluorides and alkyl chlorides would be the upper layer. Alkyl bromides and alkyl iodides are denser than water. In mixtures with water, alkyl bromides and alkyl iodides would separate into the lower layer. Increasing the number of halogen atoms increases the density of the compounds. Aryl halides are polar molecules due to the presence of the polar carbon-halogen bond, but they are less polar than alkyl halides. Aryl halides have physical properties very similar to alkyl halides. We should make special note of the isomers of dihalobenzenes. If we compare the ortho, para, and meta isomers of dichlorobenzene, we see that their boiling points are nearly the same. However, the para isomers have higher melting points. The greater symmetry of the para isomers fits better into the crystal lattice, making the para isomers melt at relatively high temperatures. Aryl halides are practically insoluble in water and are denser than water. Here is a problem for you. Arrange these compounds in increasing order of their boiling points. Let's start by drawing the structure for each compound. All the three structures contain one chlorine atom. Since the boiling point increases with an increase in the number of carbon atoms, we would expect one chlorobutane with its 4 carbon atoms to have the highest boiling point. The other 2 compounds have 3 carbon atoms each, but one chloropropane is a straight chain, while isopropyl chloride is branched. Branched molecules have lower boiling points. So, isopropyl chloride should have the lowest boiling point. 1 chloropropane is in the middle. Haloalkanes undergo 3 types of reactions. They are nucleophilic substitution reactions, elimination reactions, and reaction with metals. Before you learn about the nucleophilic substitution reactions, get to know what a nucleophile is. The word nucleophile means nucleus seeking. Essentially, a nucleophile has an unshared pair of electrons, and it can use these electrons to make a covalent bond. Nucleophiles can be thought of as Lewis bases or electron pair donors. Nucleophiles may be anions or neutral molecules. In nucleophilic substitution reactions, a nucleophile or a Lewis base substitutes for a halogen atom in an alkyl halide. Here is the general form of the reaction. The halogen is referred to as the leaving group because it leaves the alkyl halide when the nucleophile reacts. Since the substitution reaction is initiated by a nucleophile, it is called a nucleophilic substitution reaction. Common nucleophiles include the hydroxide ion and water, both of which react with alkyl halides to make alcohols. Ammonia and substituted amines are used to convert alkyl halides into amines. Note the lone pairs on each formula. Sodium or potassium salts of alkoxides can be used to make ethers from alkyl halides. Sodium or potassium salts of carboxylates can be used to make esters from alkyl halides. Sodium iodide can be used to make alkyl iodides from alkyl halides. Lithium aluminium hydride can be used to convert alkyl halides into hydrocarbons. Some nucleophiles can be described as ambident nucleophiles. These contain two nucleophilic centers and so can link to the alkyl halide in two different ways. For example, the cyanide ion can link through the carbon atom to make alkyl cyanides. If the cyanide ion links through the nitrogen, alkyl isocyanides will form. The nitride ion is another example of an ambident nucleophile. If it links through the nitrogen, a nitroalkane will form. It can also link through the oxygen to make alkyl nitrides. Depending upon the mechanism or the reaction conditions, nucleophilic substitution reactions can be classified as Sn1 or Sn2 reactions. The S is for substitution and the N is for nucleophilic. Since these reactions are initiated by the nucleophile, the number gives information on the reaction kinetics, 2 for bimolecular and 1 for unimolecular. Let's start with the Sn2 reaction. The reaction between 2-iodobutane and hydroxide ion to yield 2-butanol is an example of an Sn2 reaction. This reaction follows second-order kinetics, meaning that the reaction rate depends on the concentration of both the nucleophile and the alkyl halide. As the slow step or rate-determining step involves two molecules, the mechanism is termed as bimolecular. This reaction occurs in a single step and does not involve any intermediate. Take note of the three-dimensional arrangement of the atoms around the carbon in the alkyl halide. The solid wedge is used to show the bonds coming out of the plane of the screen. The dashed lines show bonds going down the plane of the screen, while the straight lines represent the bonds in the plane of the screen. In the Sn2 mechanism, the nucleophile attacks from the back of the molecule on the opposite side from the halogen atom, the leaving group in this reaction. The leaving group leaves simultaneously. This is described as a concerted mechanism. That is a one-step mechanism, because the new bond between the nucleophile and the carbon atom forms at the same time as that of the carbon-halogen bond breaks, as shown in the pentacoordinate transition state. Since the carbon atom is bonded to 5 atoms, the transition state is unstable and hence cannot be isolated. As the bond between the nucleophile and the carbon atom forms, the bond between the carbon and the leaving group weakens. The nucleophile essentially pushes the leaving group off the carbon atom. There is only one type of product in an Sn2 reaction. If you compare the alkyl halide reactant and the substituted product, you can see that they have opposite stereochemistry. This switch is called an inversion of configuration. Can you imagine an umbrella being pushed inside out by a heavy wind? This is a useful analogy for understanding the Sn2 mechanism. Let's apply our knowledge of nucleophilic substitution reactions to a couple of problems. Try to answer them on your own before checking the solutions. What happens when 2-bromo-octane is treated with aqueous potassium hydroxide? Start by writing out the reactants. The hydroxide ion is the nucleophile. See how it approaches the carbon atom from behind. Notice the inversion of configuration as the hydroxide ion pushes the bromide ion out to make 2-octanol. What happens when methyl chloride is treated with potassium cyanide? KCN is ionic, so it generates a cyanide ion which attacks the carbon in the methyl cyanide. In principle, the cyanide ion is ambident and could attack from either end. However, the CC bond is more stable than the CN bond. So, methyl cyanide is the primary product. If we wanted to make methyl isocyanide as the primary product, we should have used silver cyanide as the nucleophile. Since silver cyanide has significant covalent character, linking through the nitrogen atom predominates. As you've seen, the reaction involves the approach of the nucleophile to the carbon bearing the leaving group. Hence, the presence of bulky groups on or near the carbon atom will hinder the approaching nucleophile. Thus, among the alkyl halides, methyl halides, due to the presence of only 3 small hydrogen atoms, are the most reactive in Sn2 reactions. Tertiary alkyl halides, on the other hand, due to the presence of bulky groups, are the least reactive in Sn2 reactions. Thus, the order of reactivity of alkyl halides towards Sn2 reactions is as shown here. Not all leaving groups react equally well. In general, among the halogens, fluorides are the poorest leaving groups, and iodides are the best leaving groups. In these pairs of halogen compounds, which would undergo an Sn2 reaction faster? Let's start by drawing out the structures. For the first pair, 1-bromohexane is a primary alkyl halide, and cyclohexyl bromide is a secondary alkyl halide. We expect 1-bromohexane, then, to be more reactive and react more quickly. For the second pair, both structures are secondary haloalkanes. However, iodine has a weaker bond to carbon than chlorine. Alkyl iodides are much more reactive than alkyl chlorides. Now, it's time to turn our attention to the other mechanism called the Sn1 Reaction Mechanism. The reaction between 3-bromo-3-methyl-hexane and hydroxide ion to yield 3-methyl-3-hexanol can be taken as an example of an Sn1 reaction. The reaction shows first-order kinetics as the reaction rate depends only on the concentration of the alkyl halide and not on the concentration of the hydroxide ion. The reaction occurs in 2 steps. In step 1, the leaving group departs, resulting in the formation of a carbocation. This step is slow and reversible. In step 2, the nucleophile attacks the carbocation, forming a covalent bond. The greater the possibility of the formation of a carbocation by an alkyl halide, the higher are the chances for the reaction to proceed via the Sn1 mechanism. Further, the greater the stability of carbocation, the greater will be its ease of formation from alkyl halide, and the faster will be the rate of reaction. Thus, due to the greater stability of tertiary carbocations, tertiary alkyl halides readily undergo Sn1 reactions. Allylic and benzylic halides also show high reactivity towards the Sn1 reaction. This is because the allylic and benzylic carbocations formed get stabilized through resonance, as shown here. Sn1 reactions are usually carried out in polar protic solvents such as water, alcohols, and acetic acid. The proton from the solvent molecules solvate the halide ion as it leaves in the first step of the mechanism. In the Sn1 mechanism, there are two directions from which the nucleophile can attack the carbocation. Two different products can be formed from the Sn1 mechanism. Compare the product that is formed when the nucleophile approaches from the left compared to when the nucleophile approaches from the right. They have the same formula, but different arrangements in space. These two products are mirror images of each other. They are not superimposable. Even if we rotate the right-hand molecule around the bond between the black and blue atoms, it still doesn't match the left-hand molecule. We call these as enantiomers. In the Sn1 mechanism, both enantiomers are equally likely to form. This is called racemization, and such 50-50 mixtures are called racemic mixtures. You learn more about terms such as enantiomers and racemic mixtures, as well as about the stereochemical aspects of nucleophilic substitution reactions in the next module. You already know that an Sn1 reaction proceeds with a complete racemization, while an Sn2 reaction proceeds with a complete inversion. Why? In order to understand these concepts, we need to learn some elementary concepts of stereochemical principles and notations, such as plane polarized light, asymmetry, chirality, racemization, inversion of configuration, and retention of configuration. Let's start our discussion with plane polarized light and optical activity. Ordinary light is light vibrating in all directions through the line of propagation. When ordinary light is passed through a lens made of Polaroid, or more traditionally calcite, it produces a light that vibrates in only one plane and is called plane polarized light. When plane polarized light is passed through a solution of certain compounds, they rotate the plane polarized light in a specific direction. Such compounds are called optically active compounds. Let us see how this rotation of the plane of polarized light or optical activity can be detected. The angle by which plane polarized light is rotated is measured by an instrument called a polarimeter. It consists of a light source, two lenses, and a tube between the lenses to hold the substance that is being examined for optical activity. This arrangement is schematically represented as shown here. If a substance rotates plane polarized light to the right or clockwise, as seen by an observer towards whom the light is approaching, then it is called dextrorotatory or D form. It is indicated by placing a plus sign before the degree of rotation. In Greek, dextro means right rotating, and hence the term dextrorotatory. On the other hand, if a substance rotates plane polarized light to the left angle or counterclockwise direction, as seen by an observer towards whom the light is approaching, then the compound is said to be levorotatory or L form. It is indicated by placing a minus sign before the degree of rotation. In Greek, levo means left rotating, and hence the term levorotatory. For example, the lactic acid extracted from muscle tissue rotates plane polarized light to the right, and hence is known as dextrorotatory lactic acid or plus lactic acid. Similarly, the 2-methyl-1-butanol obtained from fusel oil rotates plane polarized light to the left, and it is known as levorotatory 2-methyl-1-butanol or minus 2-methyl-1-butanol. Such plus or minus isomers of a compound are called optical isomers, and the phenomenon is known as optical isomerism. According to Louis Pasteur, a noted scientist, the optical activity of a compound is associated with the three-dimensional arrangement of atoms in a molecule. The two forms of crystals of certain compounds in their aqueous solutions show optical rotation, equal in magnitude but opposite in direction. He concluded that the difference in optical activity is due to the difference in the three-dimensional arrangement of atoms in the two types of crystals. Later, a Dutch scientist, J. van 't Hoff, and a French scientist, C. Lebel, independently argued that if all the four substituents or groups attached to the central carbon atom are different, then such a carbon is said to be an asymmetric carbon or stereocenter. The resulting molecule is said to be an asymmetric molecule. This asymmetry of the molecule is responsible for optical activity. You see symmetry and asymmetry commonly in your everyday life. For example, a sphere, a cone, and a cube are identical to their mirror images and are superimposable. However, many objects are non-superimposable on their mirror images. For example, the left hand and the right hand are mirror images of each other, but they do not superimpose, and hence are said to be non-superimposable. Objects that are non-superimposable on their mirror images are said to be chiral, and this property is known as chirality. On the other hand, objects that are superimposable on their mirror images are called achiral. Let us apply this concept to organic molecules. Chiral molecules may contain one or more asymmetric carbons or stereocenters. an asymmetric carbon is represented with a star on it. Consider two simple molecules, propan-2-ol and butan-2-ol, and their mirror images as shown here. Propan-2-ol does not contain an asymmetric center, since the four groups attached to the tetrahedral carbon are not all different. Thus, it is an alkyl. However, butan-2-ol contains four different groups attached to the tetrahedral carbon. Hence, it is an asymmetric molecule and is expected to be chiral and optically active. Some common examples of chiral molecules are 2-chlorobutane, 2,3-dihydroxypropanol, lactic acid, and mandelic acid. Non-superimposable mirror image isomers are known as enantiomers. Enantiomers possess identical physical properties like melting points, boiling points, solubility, and refractive index. They only differ with respect to the direction of rotation of plane polarized light. They can either be dextrorotatory or levorotatory. If a mixture contains equimolar proportions of enantiomers, then it shows zero optical rotation. Such a mixture is known as racemic modification. A racemic mixture is represented with the symbol Dl or plus minus before the name of the compound. The process of the formation of an equimolar proportion of an enantiomeric mixture from an optically pure compound is known as racemization. Another important concept is that of retention and inversion of configuration. Retention of configuration is the preservation of the integrity of the spatial arrangement of bonds to an asymmetric center during a chemical transformation. For example, in the conversion of a chemical species XCABC to YCABC, the relative configuration of the reactant XCABC is retained in the product. In general, if there is no detachment of the bond attached to the stereocenter in the chemical transformation, then the product will have the same configuration of the groups around the stereocenter as that of the reactant or the substrate. Such a reaction is said to proceed with retention of configuration. In the reaction that takes place when -2-methylbutan-1-ol is heated with concentrated hydrochloric acid, there is retention of configuration as shown here. Inversion of configuration in a reaction yields a product whose configuration is opposite to that of the reactant or the substrate. For example, when -2-bromooctane reacts with sodium hydroxide in a reaction that follows second-order kinetics, +2-octanol with inverted configuration is obtained. You are already familiar with the reaction mechanism of nucleophilic substitution reactions of alkyl halides. An Sn1 reaction is accompanied by racemization, while an Sn2 reaction proceeds with inversion of configuration. Can you think why? we can illustrate the stereochemical aspects by taking the example of an optically active alkyl halide as a substrate. In this process, if the reaction conditions are favorable for first-order kinetics, then it follows the mechanism of an Sn1 reaction. This mechanism proceeds in two steps. In the first step, which is the slow step, the alkyl halide undergoes ionization and forms a stable carbocation intermediate. This intermediate is sp2 hybridized and has a planar geometry as shown here. In the second step, the attack of the nucleophile on the planar carbocation intermediate can take place from either face with equal ease. This results in the formation of a mixture of products in equal quantities, and this process is known as racemization. In one of these products, there is inversion of configuration, while in the other, the configuration is retained. Thus, the Sn1 mechanism is accompanied by racemization. It is clear that the formation of the inversion product is due to the attack of the nucleophile on the planar carbocation intermediate from the side opposite to that of the leaving group. On the other hand, the formation of the retention product is due to the attack of the nucleophile on the planar carbocation from the side same as that of the leaving group. An example of this type of reaction is the hydrolysis of optically active -2-bromobutane yields a mixture of plus and -2-butanol. Remember that it's a racemization process. Now, if the reaction conditions are extremely favorable for second-order kinetics, then the alkyl halides follow the Sn2 reaction mechanism. It's a concerted process. That is, it proceeds in a single step. Here, the nucleophile attacks from the direction opposite to that of the leaving group, which is also known as a backside attack. In this process, the displacement of the leaving group from the carbon atom of the substrate and the formation of a new bond with the nucleophile take place simultaneously. This results in an unstable transition state with 5 bonds. These bonds in transition state are distorted from the tetrahedral geometry of an alkyl halide. They exist as a planar spoke arrangement for a short time. Then, the leaving group is expelled and results in a product with a complete inversion of configuration. This is known as umbrella inversion. Thus, the Sn2 mechanism is accompanied by a complete inversion of configuration. An example is the reaction of -2-bromooctane with sodium hydroxide to form plus octane 2-ol with a complete inversion of configuration. You will learn about elimination reactions of haloalkanes and also their reactions with metals. Apart from undergoing substitution reactions, haloalkanes also undergo elimination reactions. In these reactions, a haloalkane with a beta hydrogen atom, on heating with an alcoholic solution of potassium hydroxide, loses a halogen atom from the alpha carbon and a hydrogen atom from the beta carbon to form an alkene molecule. Since a beta hydrogen atom is involved in the elimination, these reactions are often called beta elimination reactions. What if there is more than one beta hydrogen in the molecule? In this situation, more than one possible product can be formed. In such cases, the major product can be predicted by Zaitsev's rule or Zaitsev's rule. According to this rule, in dehydrohalogenation reactions, the preferred product is the alkene that has the greater number of alkyl groups attached to the doubly bonded carbon atoms. Let's look at an example. Looking at the reactant molecule, we see that there are two beta carbons, one on either side of the carbon attached to the chlorine atom. We could remove a hydrogen atom from either beta carbon, leading to two possible products. When we draw the structure of the two products, we see that the first product, formed when a hydrogen atom is removed from the left beta carbon, has three alkyl groups linked to the carbons of the double bond. The second product, formed when a hydrogen atom is removed from the right beta carbon, has only two alkyl groups attached to the carbons of the double bond. Thus, according to Zaitsev's rule, the first product is the preferred product. Now try a problem on your own. Predict the alkenes that would be formed by the reaction of 2-chloro-2-methyl-butane with sodium ethoxide in ethanol. Sodium ethoxide in ethanol is a strong base. Try to work out the answer independently before checking the solution. How can dehydrohalogenation by beta elimination occur in this molecule? The chlorine atom can be removed from carbon number 2. But from the structure, we see that there is a choice of two positions from which a hydrogen could be lost. Two products will form. Zaitsev's rule predicts which alkene is formed in the greatest amount. 2-methyl-2-butene has three alkyl substituents of the double bond. In comparison, 2-methyl-1-butene is disubstituted. Therefore, Zaitsev's rule predicts that 2-methyl-2-butene is the major product. An alkyl halide may either undergo substitution or elimination reaction depending on its nature and on the strength and size of the nucleophile. In the presence of a bulkier nucleophile, elimination is preferred over substitution. Due to the steric factors, the abstraction of proton is comparatively easy than approaching the tetravalent carbon for substitution. For example, primary alkyl halides have little steric hindrance, and hence readily undergo Sn2 reactions, while tertiary alkyl halides undergo Sn1 reactions due to the formation of a stable carbocation. Secondary alkyl halides, depending on the strength of the base or nucleophile, may undergo either substitution or elimination reactions. Now let us look at the reactions of haloalkanes with metals. Most organic chlorides, bromides, and iodides will react with certain metals to form compounds containing carbon-metal bonds. Such compounds are called organometallic compounds. We will discuss two classes of reactions of alkyl halides with metals. One important class of organometallic compounds is called Grignard Reagents. Grignard Reagents are alkyl magnesium halides. They have the general formula RMgX where R is an alkyl or aryl group and X is a chloride, bromide or iodide. A Grignard reagent can be synthesized by combining a haloalkane with magnesium metal in dry ether. A general equation is shown here. Grignard reagents are used in a variety of organic syntheses. For example, bromomethane reacts with magnesium in dry ether to form a Grignard reagent. Methyl magnesium bromide. In a Grignard reagent, the carbon-magnesium bond is covalent but very polar, with the carbon being more electronegative than magnesium. The magnesium-halogen bond is essentially ionic in nature. Grignard reagents are highly reactive compounds. They react with any source of proton, even with weak proton donors such as water, alcohol or amines, to give hydrocarbons. The reactions of Grignard reagents with water, alcohol and amines to form alkanes are shown here. This is one of the methods to convert alkyl halides into hydrocarbons. Since Grignard reagents readily react with water, it is very important to prevent them from coming in contact with even traces of moisture. Here's a problem for you to try. What happens when bromocyclohexane is treated with magnesium in dry ether? What will form if this product is then reacted with water? You should recognize that a Grignard reagent will be formed under these conditions. The Grignard reagent is shown in the first equation. Then, if water is present, the Grignard reagent will react to form cyclohexane.
This cake is yummy. Can you please share the recipe with me? I love baking.
Sure. For baking this cake, I use 2 eggs, a cup of flour, a cup of sugar, and a cup of butter.
If I have 6 eggs, can I bake a bigger cake?
6 eggs are too many. For this cake, follow the proportion. If you want a bigger cake, increase the ingredients in the same proportion.
In nature too, you will find substances combined in fixed proportions. For instance, the law of constant proportions and the law of multiple proportions explain how various elements combine to form different compounds. This lesson is about laws of chemical combination and an introduction to an atom. At the end of this lesson, you will be able to explain the law of conservation of mass, describe an experiment to prove the law of conservation of mass, explain the law of constant proportions, explain the law of multiple proportion, list the postulates of Dalton's atom, define an atom, identify the symbols of elements, identify the atomic mass of elements, define a molecule, identify the atomicity of elements, define an ion, define valency, list the rules for writing a formula, and apply a set of rules to write a formula. After a series of experiments, Democritus concluded that if you continue to cut a stone into smaller and smaller pieces, at some point you would reach a piece so tiny that it could no longer be divided. Democritus called these infinitely small pieces of matter atomos, meaning indivisible. Convinced that matter is made of tiny indivisible particles. Many scientists like Evangelista Torricelli, Daniel Bernoulli, Joseph Priestley, and Antoine Lavoisier started studying the natural world. Among them, Joseph Priestley discovered that substances could combine together or break apart to form new substances. Later, Antoine Lavoisier, from his experimental observations, established a law that states that there is no gain or loss of mass when new substances are formed. This can be better explained with the help of an experiment. To do this experiment, take 5 grams of iron filings in a watch glass. Take 5 grams of sulfur in another watch glass. Then mix the iron filings and the sulfur thoroughly and weigh it. The weight is 10 grams. Now heat the mixture. It forms a dark molten mass of ferrous sulfide. Weigh it. You'll find the weight to be 10 grams. This shows that the mass is the same, though there is a change in form. Therefore, the law of conservation of mass can be stated as: in any chemical reaction, the total mass of the substance before and after the reaction is the same, although its matter undergoes a physical change. The total mass of reactants is equal to the total mass of products. This led scientists to ponder over the combination of substances, and they conducted various experiments. All these observations were accepted, and the law of definite proportion was proposed by Proust. Proust, a French chemist, concluded that when 100 grams of water was decomposed, 11 grams of hydrogen and 89 grams of oxygen was obtained. He later purified and analyzed numerous compounds and concluded that every pure substance contains the same elements combined in the same proportions by weight. So, the law of definite proportions can be defined as: in a chemical substance, the elements are always present in definite proportions by mass. Hydrogen and oxygen can combine in different proportions to form different compounds like water and hydrogen peroxide. 2 parts of hydrogen combine with 1 part of oxygen to form water, and 2 parts of hydrogen combines with 2 parts of oxygen to form hydrogen peroxide. This follows the law of multiple proportions. According to this law, when 2 elements combine to form 2 or more different compounds, then the weight of one of the elements is constant and the other has a simple ratio. Basing on Proust's observations, John Dalton further researched and realized that water could exist as a gas that is mixed with air and occupies the same space as air. Solids cannot occupy the same space as gas. For example, ice cannot mix with air. This made Dalton ponder over what could allow water to sometimes behave as a solid and as a gas at other times. After a series of experiments with various substances in different states, Dalton concluded that all matter must be composed of tiny particles which cannot be further divided. He called them atoms. So an atom can be defined as the smallest particle of an element. According to Dalton, all matter is made of atoms. Atoms are indivisible and indestructible. All atoms of a given element are identical in mass and in properties. Compounds are formed by a combination of 2 or more different kinds of atoms. And a chemical reaction is a rearrangement of atoms. Having identified some elements, Dalton proposed a scheme of notation to represent elements. For example, hydrogen was represented as carbon as, oxygen as, nitrogen as, sulfur as, phosphorus as, copper as, silver as, gold as, iron as, chlorine as, tin as, zinc as, and lead as. The symbols used today were suggested by Berzelius. The first letter of the symbol is always in uppercase. Some elements were represented by the starting alphabet of its name. For instance, carbon is represented as C, boron as B, oxygen as O, sulfur as S, nitrogen is written as N, and hydrogen as H. All the elements do not follow the same convention. Symbols of some elements were the first two alphabets, but the second alphabet is in the lower case. For example, aluminium is represented as Al, chlorine as Cl, argon is written as Ar, beryllium as Be, and lithium as Li. An element is represented by either the first or the first and any other letter of its Latin name. There are some exceptions while writing the symbols for some of the elements. These names were derived from Latin. In general, the first letter and the second letter of their Latin names are used to represent the symbols of these elements. For example, antimony is called stibium in Latin, and the symbol is Sb. Copper is known as cuprum, and the symbol is Cu. Gold as ornament, represented by Au. Iron as ferrum, and the symbol is Fe. Lead as plumbum, and is represented by Pb. Mercury as hydragium, and is represented as Hg. Kalium is the Latin name of potassium, and its symbol is K. Silver as argentum, and it is represented as Ag. Natrium is the Latin name of sodium, and is represented as Na. The Latin name of tin is stannum, and the symbol is Sn. Wolfram is the Latin name of tungsten, and it is represented as W. A symbol not only represents one atom, but also the mass of the element. According to Dalton, each element has a characteristic atomic mass. Scientists initially took the mass of oxygen as standard mass, since oxygen formed a large number of compounds. In 1961, carbon-12 isotope was chosen as the standard reference for measuring atomic masses. The relative atomic masses of all elements have been found with respect to an atom of carbon-12. For example, in a bakery, if a cake is cut into 12 equal pieces, he is able to find the mass of each confectionery item relative to the mass of a single piece of cake. Now, he sells the confectionery by relative confectionery mass unit. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom as compared to 1/12 the mass of one C12 atom. Matter is made of atoms. But how do these atoms exist? These atoms exist in a combined state called molecules. Thus, a molecule is the smallest particle of an element or compound that can exist independently and show all the properties of that substance. Some elements like sodium, potassium, and helium exist as single atoms, and others like hydrogen, oxygen, etc. exist in a combined state. Atoms combine to form molecules. The molecules of an element are constituted by the same type of atoms. For example, elements like hydrogen, oxygen, phosphorus have more than one atom in a molecule. This number is specific for an element and is known as its atomicity. Thus, the number of atoms constituting a molecule is referred to as atomicity. Let us look at some examples. An oxygen molecule has 2 atoms of oxygen and is known as a diatomic molecule. Hydrogen, chlorine, nitrogen, etc. also exist as diatomic molecules. Elements like phosphorus and sulfur have more than 2 atoms in a molecule and are called polyatomic. A phosphorus molecule has 4 atoms of phosphorus, P4, and a sulfur molecule has 8 atoms and is octaatomic, S8. So far we have discussed about the molecules of elements. Elements combine to form compounds. Thus, a molecule of a compound has 2 or more elements. For example, common salt is a compound of sodium and chlorine, where sodium is a positively charged particle and chlorine a negatively charged particle, and each of this is called an ion. Thus, a charged particle is called an ion. The positively charged particle is called cation. On the other hand, the negatively charged particle is referred to as anion. We know that atoms of an element combine to form a compound. Every atom has a specific combining capacity. This combining capacity of an element is known as valency. For example, consider a water molecule. It has 2 atoms of hydrogen and 1 atom of oxygen. This shows that the combining capacity of oxygen is 2 and takes 2 hydrogen atoms. Similarly, sodium monoxide has 2 atoms of sodium and 1 atom of oxygen. Thus, the combining capacity of sodium is 1 and oxygen is 2. Here the compound is formed by 2 different elements, and such compounds are called binary compounds. Some compounds have more than 2 elements or a group of elements as ions. For example, an OH ion. It consists of hydrogen and oxygen atom, and its valency is 1. Here are the valencies of some elements. Chlorine has the valency of 1. The valency of magnesium and calcium is 2, while nitrogen and aluminium is 3, and that of carbon is 4. A nitrate ion and an ammonium ion show a valency of 1, whereas carbonate and sulfate have a valency of 2. The knowledge of valency helps to write the formulae of compounds. A formula is the shorthand representation of a compound. For example, consider a water molecule. It has hydrogen and oxygen. The symbol of hydrogen is H and oxygen is O, and its formula is H2O. Let's learn to write a formula. To write the formula of compounds, we follow a set of rules. Let us write the formula of calcium carbonate. First and foremost, identify the elements present in calcium carbonate. They are calcium, carbon, and oxygen. Identify the cation and the anion. In calcium carbonate, calcium is the cation and carbonate is the anion. Next, identify the valency of the cation and the anion and place it just above the symbol. For example, the valency of calcium is 2 and the valency of carbonate is also 2. Then cross-multiply the valencies. Now write the numerals as subscript right after the respective symbol, Ca2 and CO32. In case of calcium carbonate, both the valencies are 2, hence the formula is CaCO3. For compounds formed with polyatomic ions, the ion is enclosed in a bracket before writing the number of units. For example, ammonium sulfate. It has both ammonium and sulfate ions. The valency of an ammonium ion is 1 and sulfate is 2. When we cross-multiply, ammonium has a subscript 2. This 2 is written outside the bracket. There is an exception for some of the metals, which exhibit variable valency and are named accordingly. For example, copper shows 2 different valencies, 1 and 2. In such a case, the compound formed with lower valency is called cuprous, and the compound is cuprous oxide, that is Cu2O. On the other hand, copper with valency 2 forms cupric oxide, CuO. Similarly, iron also exhibits variable valency. Iron with a valency of 2 is ferrous, and iron with a valency of 3 is ferric.
I wonder, what's the maximum I can score in this game?
You can't score more than the total of the ball points, as the number of balls in this game is fixed. Similarly, based on the study made by different scientists on an atom, concluded that any atom is made of fixed number of charged particles called protons and electrons. This lesson is about the internal structure of an atom. At the end of this lesson, you will be able to define atomic number, define subshells, determine the electronic configuration of an element given its atomic number, determine the valency of an element given its electronic configuration, explain the concept of a neutron based on Chadwick's work, define atomic mass, define isotopes and isobars, and list the applications for isotopes. Scientists propose that an atom is made of 2 kinds of particles. The positively charged particles are protons, and the negatively charged particles are electrons. Every atom of an element has a fixed number of protons in its nucleus. This fixed number of protons is referred to as an atomic number. This number is constant for an element. It is represented by an alphabet Z. Moreover, the number of electrons in an atom of an element is also equal to the atomic number of the element. For example, if the atomic number of an element is 12, then its atom contains 12 protons and 12 electrons. In an atom, electrons are not randomly placed around the nucleus, but they are placed in fixed energy levels called shells, as per Bohr's atomic model. These shells are named K, L, M, N. The arrangement of electrons in these shells is known as electronic configuration. For example, carbon has 6 electrons. Its electronic configuration is 2, 4. 2 electrons are placed in K shell and 4 electrons in L shell. In order to write down the electronic configuration of an element, one should have knowledge about the number of electrons in one atom of the element and the maximum number of electrons that can be accommodated in different shells of the atom. The maximum number of electrons that can be accommodated in any energy level of the atom is given by a formula 2n to the power of 2, where n is the number of that energy level. For example, the number of electrons present in the first energy level, n equals 1. According to the formula, 2 multiplied by 1 to the power of 2 equals 2. So, the maximum number of electrons present in the first energy level is 2. According to Bohr's model of an atom, the first energy level K can have 2 electrons. The maximum number of electrons which can be accommodated in shell L is 2 multiplied by 2 to the power of 2 equal to 8. Similarly, for M and N shells, the maximum number of electrons that can be accommodated are 2 multiplied by 3 to the power of 2 equals 18, and 2 multiplied by 4 to the power of 2 equals to 32 respectively. During the arrangement of electrons in the shells, the outermost shell of an atom cannot accommodate more than 8 electrons, even if it has the capacity to accommodate more electrons. Generally, the outermost shell of an atom can have a maximum of 8 electrons only, even though it has the capacity to accommodate 18 electrons. This is due to the fact that having 8 electrons in the outermost shell makes an atom stable. There is an exception. If the outermost shell is the first shell or K shell, the shell can hold only 2 electrons. For example, helium has only 1 shell in its atom. Electrons in an atom do not occupy a new shell unless all the inner shells are completely filled. The filling of electrons in an atom is a stepwise approach. First, the electrons are filled in K shell, then in L shell, M shell, N shell, and so on. There are few exceptions to this rule, which are applicable to elements with an atomic number more than 18. After a series of experiments and a detailed study by scientists like Louis de Broglie, Schrödinger, Sommerfeld, etc., it was proved that shells have energy levels within them and are subshells. These subshells are S, P, D, and F. Electrons are distributed in these subshells. Every subshell can accommodate a fixed number of electrons. The S subshell can hold a maximum of 2 electrons, a maximum of 6 electrons in the P subshell, 10 electrons in D, and 14 electrons in F. Electrons are distributed in their respective shells and subshells. The first energy level, K, can have one subshell which can accommodate 2 electrons. The next shell is the L shell, which contains S and P subshells, where the S subshell accommodates 2 and P shell 6 electrons. M is the third shell and have S, P, and D subshells which accommodate 2, 6, and 10 electrons respectively. Next is the N shell with S, P, D, and F subshells accommodating 2, 6, 10, and 14 electrons respectively. Let's observe the distribution of electrons in the given 20 elements. Electrons in an atom are arranged in definite shells. The electrons which are present in the outermost shell of an atom are referred as valence electrons. From the Octet Rule, an outermost shell of an atom can accommodate 8 electrons. It was observed and concluded that an atom with completely filled subshells are stable and do not react easily In other words, it means that the combining capacities are 0 or nil. The outermost shell of inert gas elements whose subshells are completely filled are stable. For example, helium and neon, where helium has 2 electrons in its outermost shell and all other inert gas elements have 8 electrons. The combining capacity of the atom to form molecules either with the same or different elements is defined as valency. For example, elements like hydrogen, lithium, and sodium atoms contain 1 electron in the outermost shell. Therefore, they can lose 1 electron. So their valency is 1. If atom contains less than 4 electrons in its outermost shell, the valency of an atom is equal to the number of electrons present in the valence shell. For example, aluminium has 3 electrons in its outermost shell, so the valency of aluminium is 3. On the other hand, if the outer shell has more than 4 electrons, the valency is 8 minus the number of electrons in the outer shell. For example, chlorine atom has 7 electrons in the outermost shell. Here, in this case, it is easier for chlorine to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet, which gives the valency of 1 for chlorine. Let's examine the element helium. It was found that helium has 2 protons and 2 electrons. However, its mass was found to be 4 times that of hydrogen. Similarly, the weights of some other elements were also found to be double or more than double the weight. For example, the number of protons in chlorine is 17, but its mass was found to be 35. Similarly, number of protons in mercury is 80, but its mass was found to be 200. This problem was solved when James Chadwick discovered another particle, neutron. Neutron is a neutral particle with a mass equal to that of a proton and is present in the nucleus along with the proton. An interesting aspect came into picture after the discovery of a neutron by Chadwick. Till then, only the atomic number of an element was in existence, which referred to the number of protons present in the nucleus of an atom. The total mass of the protons and neutrons inside the nucleus was regarded as the atomic mass of an element. Therefore, atomic mass can be defined as the total number of protons and neutrons present in one atom of an element. For example, one atom of sodium element contains 11 protons and 12 neutrons. So, the atomic mass number of sodium is 11 plus 12 equals 23. The mass number is denoted by an alphabet A. Now, let's try to derive a relationship between mass number and atomic number. Mass number equals the number of protons plus number of neutrons. Since the number of protons in an atom is equal to the atomic number of the element, the above relation can be rewritten as mass number equals atomic number plus the number of neutrons. The atomic number and mass number can be indicated on the symbol of an element. The atomic number is written as subscript on the lower left side of the symbol, whereas the mass number has a superscript on the upper left side of the symbol. Normally a carbon atom has 6 protons and 6 neutrons, but some unstable carbon atoms were found. These carbon atoms had 6 electrons, but the nucleus was similar to that of a nitrogen atom and it had a mass of 14. Soddy discovered that certain elements had a heavier mass. Their atomic number and chemical behavior was same, but their mass was slightly higher. The higher mass is due to the presence of extra neutrons. Soddy called the elements with same atomic number and different mass number as isotopes. Greek meaning same place. Thus, isotopes are atoms of the same element with the same atomic number but a different atomic mass. The valency of isotopes is the same. Isotopes of the same element differ in their physical properties. For example, 12C6 and 14C6 are isotopes of carbon. 1H1 protium, 2H1 deuterium, 3H1 tritium are isotopes of hydrogen. 35Cl17 and 37Cl17 are isotopes of chlorine. The chemical properties of all the isotopes of an element are the same. This is due to the presence of same number of electrons. Rarely some isotopes have special properties which were found to be useful in various fields. For example, an isotope of uranium is used as fuel in a nuclear reactor. An isotope of cobalt is used in the treatment of cancer. For treating goiter, an isotope of iodine is used. In some cases, it is also possible that the atoms of different elements have different atomic numbers, may have the same mass number. Such atoms are called as isobars. For example, argon with atomic number 18 and calcium with atomic number 20. The number of electrons in these atoms are different, but the mass number of both these elements is 40. We observe changes in properties and forms of substances around us all the time. For example, changing of coal when it is burned to produce heat, changing of milk into curd, and rusting of iron when exposed to moisture. All these changes are a result of chemical reactions. These chemical changes can be represented through chemical equations. In this lesson, you will learn about writing and balancing chemical equations. At the end of this lesson, you will be able to define a chemical reaction, explain the symbolic representation of a chemical reaction, identify the components in a chemical reaction, explain how to write a chemical reaction, and balance a chemical reaction. Let us see what a chemical reaction is through an experiment. We begin with some zinc granules in a conical flask. These granules are blue-gray in color. Fit a 2-holed rubber cork on this flask. Then we fit a thermometer into one hole of the cork and a thistle funnel into the other hole. Next, pour 5 ml of dilute sulfuric acid into the conical flask through the thistle funnel. The color of the zinc granules changes from blue-gray to white. Some gas bubbles are also released from the solution. This is because zinc reacts with sulfuric acid to form zinc sulfate and hydrogen gas. Zinc sulfate is white in color. The thermometer shows an increase in the temperature of the solution. Therefore, as you saw in this experiment, the color of zinc changed during the reaction. That is, there was a change in physical properties. The reaction also resulted in the evolution of a gas. That is, the form of the reactant changed. Zinc reacted with sulfuric acid to form zinc sulfate, a salt. Thus, the composition of the reactants changed. Hence, we can say that a chemical reaction involves the change in the physical and chemical properties, the composition and the physical state of a substance, whether an element or a compound. A chemical reaction is typically expressed in terms of a chemical equation. A chemical equation indicates the components in a reaction, the physical state of each reactant, and the products of a reaction. Thus, a chemical equation is a symbolic representation of the reactants and the products, using their chemical formulae. For example, zinc reacts with dilute sulfuric acid to form zinc sulfate and hydrogen gas. This is represented in the form of an equation, as shown here. Solid zinc reacts with dilute sulfuric acid to form an aqueous solution of zinc sulfate and hydrogen gas. A chemical equation is made up of the following components. The reacting substances, known as reactants, are on the left-hand side. For example, in the equation you just saw, zinc and dilute sulfuric acid are the reactants. Therefore, they are on the left in the equation. The resulting substances, known as products, are on the right-hand side. For example, in the equation, zinc sulfate and hydrogen gas are the products. Hence, they are on the right. An arrow separates the reactants and the products and also indicates the direction of the reaction. Thus, in the reaction you saw, the arrow indicates that zinc and sulfuric acid react to form zinc sulfate and hydrogen. Let's take another example that involves two substances. In the burning of coal, carbon reacts with oxygen to form carbon dioxide. In this reaction, carbon and oxygen are the reactants and carbon dioxide is the product. The chemical equation for this reaction is as shown. Solid carbon reacts with oxygen gas to form carbon dioxide gas. In chemical equations, you denote a solid with S, a liquid with L, a gas with G, an aqueous solution as AQ, a gas produced with an arrow pointing upward, precipitate formed with an arrow pointing downward. The reactants and products are separated with an arrow which points in the direction of the reaction. Let us consider the reaction of iron with steam. Solid iron reacts with steam to form solid iron oxide and hydrogen gas. This reaction is represented as shown. A symbolic representation of a chemical reaction is the first step in writing a chemical equation. The next step is to ensure that the equation is balanced, considering the law of conservation of mass. The law of conservation of mass states that the total mass of the reactants and the products should be equal. This means the number of atoms of an element on the reactant side should be the same as the number of its atoms on the product side. All chemical equations must adhere to the law of conservation of mass. Therefore, all chemical equations need to be balanced. The process of balancing a chemical equation involves 4 steps. Determining the reactants and products in a reaction. Counting the number of atoms of each on both sides. Selecting the elements that occur for the least number of times in the equation. Balancing typically starts with such elements where the number of atoms is not equal on both sides. Changing the coefficient of the molecules of reactants or products as required. You should continue balancing the atoms in this manner till you have covered all the elements in the equation. In the end, do a final check to confirm that the number of atoms on the reactant side and the product side have been properly balanced. Here is a word of caution. When you balance equations, use coefficients only on the left of the symbols of elements and compounds. Never change the formula of a compound or an element to balance an equation. To understand how an equation is balanced, let's refer back to the reaction of hydrogen with oxygen to form a molecule of water. We need to balance the equation for this reaction according to the law of conservation of mass. The first step is to determine the reactants and the products in the equation. Here, hydrogen and oxygen atoms are the reactants. Therefore, they are written on the left-hand side. The water molecule is the product, and hence it is written on the right-hand side of the equation. In the second step, you need to count the number of atoms of each type. You'll notice that hydrogen has 2 atoms on the reactant side and 2 atoms on the product side. But oxygen has 2 atoms on the reactant side and only 1 atom on the product side. So there is 1 oxygen atom less on the product side. According to the law of conservation of mass, the number of atoms on the reactants and product side should be the same. In step 3, you need to select the element that occurs in the minimum number of places in the equation. You can see that there are 2 hydrogen atoms on each side, while there are 2 oxygen atoms on the left-hand side and only 1 on the right-hand side of the equation. Hence, oxygen has to be balanced first. Finally, in step 4, you change the coefficient of the molecules of the reactants or the products. To do this, you need to first select the oxygen atom and balance it by placing the coefficient 2 before the product H2O. Now there are 2 oxygen atoms on the reactant side and 2 on the product side. However, placing the coefficient 2 before H2O gives 2 hydrogen atoms on the reactant side and 4 hydrogen atoms on the product side. Thus, there is an imbalance in the number of hydrogen atoms. To balance the hydrogen atoms, place the coefficient 2 on the left hand of hydrogen on the reactant side. Now, let's take a look at the final equation. The atoms of each element on the left and on the right hand side of the equation are now balanced as per the law of conservation of mass. According to the final balanced equation, 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. Let's practice further on balancing equations with another example. This equation deals with the combustion of ethyl alcohol. Again, the first step is to identify the reactants and the products. Here, ethyl alcohol and oxygen are the reactants, and they are written on the left-hand side of the equation. The products on the right-hand side are carbon dioxide and water. Step 2 is to check the number of atoms of each type on either side. Here we have 2 carbon atoms on the left-hand side, but only 1 on the right-hand side. 6 hydrogen atoms on the left-hand side, but only 2 on the right-hand side. 3 oxygen atoms on the left-hand side, as well as on the right-hand side. Let us begin balancing the equation by selecting carbon. There are 2 atoms of carbon on the reactant side, but only 1 atom on the product side. So to balance this, add the coefficient 2 before carbon dioxide on the right-hand side. Now, let's consider the next element, hydrogen. There are 6 atoms of hydrogen on the reactant side and 2 atoms on the product side. To balance this, you need to place the coefficient 3 before H2O on the product side. Now, as you can see, hydrogen has been balanced. The next element in the equation is oxygen. There are 7 oxygen atoms on the product side, but only 3 atoms on the reactant side. To balance the equation, place the coefficient 3 before oxygen on the left-hand side. In the end, do a final check to confirm that the number of atoms on the reactants and the product side is properly balanced. Here is what you get as the final equation. Ethyl alcohol reacts with 3 molecules of oxygen to give 2 molecules of carbon dioxide and 3 molecules of water.